Thank you for that introduction. I want first to thank the organizer for inviting me to and giving me the opportunity to talk about this preliminary work about multi-frequency inverse scattering problems. Just want to mention this is the same idea as in the talk of nice talk of Guillaume. The idea is to stabilize the inverse problem. So the idea in the talk of Guillaume, it was to couple different waves to enrich the data, to have more data, and from that the data we can get a very stable inversion. So the idea here is to use multi-frequency data, and the motivation is the following: is the uncertainty principle, and everyone. I don't know if it works. Everyone working in optics knows that there is a diffraction limit. If you try to image an object with a wavelength, with a wave that has a wavelength lambda, you cannot. There is what we call the diffraction limit. You cannot distinguish, for example, between two objects that are at distance less than the wavelength over 2. So the idea, I found this paper which explains well this uncertainty principle. The idea is to use this uncertainty principle to first to somehow to see in inverse scattering problem how can we read this property in the inversion, and the second thing is to use this observation to improve the inversion. So this is the principal idea. So I will start with this example. If you have a source function S that generates a wave propagating in a homogeneous media, and these waves you can be divided into two parts. The first part is what we call the propagating waves. These propagating waves can be detected in the far region. What I mean by far field is a few wavelength distance from the object, from the source function, and these propagating waves contain the lowest spatial frequency of the source function. And the other part is evanescent. You cannot measure them far away from the source function. And these evanescent waves are related to the high spatial frequency of the source function. So if at fixed frequency, if you try to reconstruct this source function from the measured wave far away from the source, at fixed frequency you cannot measure these evanescent waves. So you lose these information about the high frequency modes of the source function. This is the idea behind the uncertainty principle. So I will first talk about an inverse source problem. Take this source function, try to solve the problem, and show you that if you take measurement at different frequency, probably you can improve. You can convert the ill-posedness to well-posedness. You can move from logarithmic stability to linear stability. So this is the outline of the talk. So in the first part, I will talk about the inverse source problem. I will talk a little bit about uniqueness, and once we have the uniqueness, we can look on the stability problem. I will also give some numerical illustration, and then I will move to a different problem, but very close to the inverse source problem, which is the inverse medium problem. And I will give you a new result about stability estimate for the inverse medium problem with multiple frequency measurement based on the trace formula, the 1D trace formula. So this is a inverse source problem that I will consider. RD is space, D is dimension. We have the Helmholtz equation, the source function on the right side. So this source function generated the wave u everywhere outside. K will be the frequency of the wave number, and it has to be U, and we assume that source function has a compact support in a ball, center 0 and radius R0, and we assume that we take the measurement, assume that omega has the boundary gamma. Gamma is far away from the compact support of the source function. The distance between them is strictly positive. In practice, D0 has to be larger than few wavelengths. And the inverse multi-frequency inverse source problem is to reconstruct the source function from the field UK, from the wave outside the region omega, for a band of frequency, okay, between 0 and K0. So it have many results about the inverse source problem for fixed frequency or for multiple frequency measurement. I think the work which is probably the closest to my result is the work of Ehler and Valdivia. They considered multi-frequency measurement, and they took the measurement exactly at the Dirichlet eigenvalue of the Laplacian in the domain omega. And they proved the uniqueness of the inverse source problem. So we, because the media I considered here is homogeneous, I will introduce this Green function for the Helmholtz equation in the whole space. In dimension 2 is the Hennenfent function. In dimension 3 is this exponential function. And we can easily write this wave u as a convolution between this Green function, the whole space, and the source function. We denote nu is the normal derivative on the boundary of omega. And we know that if you know u outside plus the radiation condition, you can recover the normal derivative of u on gamma. So here now, from now, we assume that we have u and the normal derivative of u on the boundary. And we consider these integral operators that goes from L2 of the compact support of the source function to the L2 of the boundary gamma. And L1 will assign the Dirichlet, the trace of the wave solution on gamma, and L2 will assign the normal derivative of the wave on the boundary gamma. And the multi-frequency inverse source problem can be reformulated in this form to find the source function in L2 of the ball center 0 and radius R0, such that L1 of S is exactly u on the boundary gamma, and L2 of S is exactly the normal derivative of u on gamma. These are the data, okay, for all the frequency between 0 and K0. Okay. So, so it should be noted that at fixed frequency, if you consider only here one frequency, we don't have uniqueness. There is no uniqueness. The kernel of this system is not empty. And it's known that this inverse problem is ill-post. A small error in the measurement can produce a large error in the reconstruction. And this is because L1 and L2 are compact operators. See that because we are far away from the compact support of the source function, these kernels are smooth, and so we have compact support. We have a compact operator, and here we studied the singular eigenvalue of these operators, and we can see that they have exponential decay. Okay, so we have exponential decay of these singular eigenvalue. This means that if you want to reconstruct the high Fourier mode of the source function, you have really to deal with these small, very small singular eigenvalue. Okay, and if you invert these integral operator, these small singular eigenvalue will amplify the error in the high Fourier mode of the source function. So the one idea is to consider multi-frequency measurement, to consider measurement on a band of frequency, and we will see that this will stabilize the inverse problem. So this is the idea. The idea is to, because again the media is homogeneous, we just take a plane wave. We know that these functions are dense, the solution of the Helmholtz equation. by the way. And if we multiply the equation, the Helmholtz equation, by this plane wave, with the norm of the psi here is exactly the wave number of the frequency. We integrate by part, and we found out that we get exactly the Fourier transform of the source function. We see here, if you modify the direction, we'll get exactly the Fourier transform on the circle of radius k. This is what you get from measurement at fixed frequency. Okay. So if you go back to the signal theory, you know, if you have the Fourier transform of signal at one frequency, we know that this inverse problem is E-post. We don't have uniqueness. So it's easy to find out how the inverse source problem at fixed frequency is E-post in this case. So here we collect the data on the boundary for band of frequency. So the multi-frequency inverse source problem can be reformulated again as this. If you have the Fourier transform, if you have the k between 0 and k0, it means that you can recover the Fourier transform of the source function on a ball of radius k0. So the question is, can you recover a function which has a compact support from its Fourier transform on a ball? Okay. So, of course, you have the uniqueness. You don't need to have an interval of frequency here. You just have a sequence with that is convergent to have the uniqueness. And because this is the Fourier transform of the source function is band-limited function, it's a holomorphic function in terms of psi. So we have this easy proof of uniqueness. And we have also this stability result, which is a little bit more complicated to prove. So we assume that you have the data on the boundary. This is the normal derivative of the solution. And here you have this psi is u. I'm sorry. Again. So if you assume that because the inverse source problem that I present here is linear, so assume that this is the error on the boundary. So assume that the error is very small compared to 1 in this norm. And we assume that we are looking for a source function that is in in a ball dimension in C1 norm. And here we, in fact, the constant that we need to consider is K0, R0. With K0 is the largest frequency in the band of frequency, and R0 is the radius of the ball containing the source function. This is the term that we need to consider in the stability estimate. But we assume that here we assume that the R0 is 1. This result, okay, and you see that this is a unitless parameter. We assume that R0 is 1. This is what I did here. Is the compact R0 is equals to 1, and I will play with K0 to move from some logarithmic stability to linear stability. If K0 is very large, it means that you have the Fourier transform of the function almost everywhere. Of course, you have the Lipschitz stability. This is very easy to prove. But if K0 is very small, what happens? But you have this logarithmic stability. Of course, the constant will blows up if K0 goes to 0. Of course, you cannot reconstruct the source function from its mean. K0 goes to 0, it means that you have only the average of the source function. But we have this stability. It says that the problem is ill-post. If K0 is very small, if you do measurement in a very small band of frequency, and you have this instability. So you see here, if you take more and more measurement, larger frequency, you can stabilize the problem, the inverse source problem. You can move from logarithmic stability to linear stability. This is what I try to convince you. And this is the proof of the result. It's not obvious, but it's not too difficult too. The idea is to take a mask function. This technique has been used a long time ago by engineering. take the C infinity function, it's compact support, and with mean equals to 1 exactly. And you construct this approximation of the source function in this way, with delta n exactly this function that approximates the delta function when n goes to infinity, and times this function, which is a band limited function. But this band limited function will give you a compact support in the Fourier space. Okay. So you take the convolution of this function with the source function. This gives you a good approximation of the source function. And if you move in the Fourier space, this function Hn has a compact support exactly the compact the bar where you are taking the measurement. Okay. As you see here, if the source function is bounded by m in C1 norm, so we can easily prove this result, which is approximation of the source function in the X space, in the S space, and you have n power 1/4. And if delta here is a constant between 0 and 1/2, take 1/4, 1/4, for example, and the price you pay in approximating the source function this way is the bound of this function in the C0 norm will blows up, will goes to infinity as n goes to infinity, of course. And it blows up exponentially. Okay. If you combine both, you take S, you write S like S minus Sn plus Sn. Okay. And you use this approximation, this estimate, both estimate, you will get exactly the stability estimate that I showed here. Okay. Let's move to the numerical illustration. So the idea is to the following, and it works pretty well, not only for the inverse source problem, but also for the inverse medium problem. And the idea is to take the interval of frequency, take, for example, from k min to k max. Assume that you have many measurements here in this interval. Okay? And the idea is to move from the lowest frequency to the highest frequency. Okay. You start from the lowest frequency, try to solve the inverse problem. For example, you take the iterative method here, different iteration, and you move from you start with initial guess, like a constant function, and you solve the problem. If k min is very small, of course you will have a good approximation of the low frequency of the source function, and you move at each iteration. You try to find the best, try to reconstruct the source from the best, and you move on until you reach the highest frequency, and the highest frequency will have a good approximation of the source function. So this is the idea. This is the source function that I want to reconstruct, and the boundary frequency is k min k plus. We start with k min equals to 1, and this is the source function that I want to reconstruct. We have 4 bumps. This is the contour plot of the source function. Now we start with k equals to 9. Now we see the reconstruction, you cannot see any bumps. This is the average of the source function. And then you increase the frequency. K equals to 17, 25, 33, 31, 61. And 61 will cover completely the source function. You can also find other examples on this paper. So this is the idea. So try to, if you can measure, you can have a measurement at multiple frequency, you can probably stabilize your inverse scattering problem by using this type of measurement. And it seems that it's very easy to, in many applications, many inverse scattering problems, it seems that it is very easy to change the frequency in many applications. So if you can get multiple frequency, probably you can stabilize your inverse problem. Let's move now to the inverse medium problem. This is 1D problem just to avoid the geometrical assumption. Just want to prove that it can work for the inverse medium problem in 1D. So this is the Q. The Q is the medium function, has a compact support in 0, 1, interval 0, 1. Phi will be the total field, satisfying this Helmholtz equation. 1 plus Q will be the square root, is the index of refraction. And for any real K, we look for a solution in this form. With this term will be the incident wave on the right side or left side. Just to give you a picture of the problem. So Q of X has a compact support here, and you send wave here in these two possible directions. You have two incident directions, no more, in 1D, plus K or minus K. And for each direction, you have a scattered wave, psi. Psi plus or psi minus. And you have these radiation conditions to fix the direction of propagation of these waves. And in fact, because Q is 0 outside 0, 1, we can write the scattered wave vector like this. On the left side, mu plus. This is the reflected coefficient corresponding to the incident wave exponential ikx. And psi minus, you have mu minus is the reflected coefficient in the other direction. And the inverse medium problem here is to reconstruct the refractive index, the function Q of X, from these reflection coefficient, one of these two reflection coefficients, for a band of frequency K between 0 and K0. This is the inverse medium problem that we consider. And it seems that it's easier to work with the impedance function. So I will introduce the impedance function. Impedance functions are exactly the ratio between the derivative of the total field over ik times the total field. And I can divide by this function. We can show that it's different from 0 for all k real. These impedance functions satisfy this equation. This is Riccati equation, dimension 1. And you see here you have almost an inverse source problem, but you have this power here. It's a nonlinear problem. It's no more linear. And you normalized on the left side for p minus at 0, and you normalize on the right side for p plus. And the d minus and d plus are related to the reflected coefficient mu minus and mu plus in this formula. So if you have mu minus or mu plus, you can recover d plus or d minus as a function of k. So we can reformulate this inverse problem, 1D inverse problem. You have one of these two coefficients for a band of frequency, try to reconstruct the refractive index. And of course, for a fixed frequency, this problem is ill-posed. We don't have uniqueness. Of course, we don't have stability. So it has been a lot of papers on this work. I think that the idea is inspired by this paper. I will talk later about this problem. I think the multi-frequency inverse medium problem in 2 and 3D is still open. So let's move to the result. So this is the main result. So we consider a ball of radius m and center Q0. Q0 is a medium function, fixed medium function. In this space, Cm, m is the regularity of the medium function. And we assume that we have two medium functions, Q and Q tilde. In this ball, this is Q0, sorry. And if you assume, 0, I'm sorry, this is 0. If you assume that Q and Q tilde are lower bounded by Q0, larger than -1, and if you have D plus and D tilde plus are the measurement related to Q and Q tilde respectively, and you can prove that there exists constant CMQ0 and KMQ0 such that the difference between the two mediums is bounded by constant, does not depend on the measurement, times the difference between the measurement on L1 minus K0, K0, plus something that is very small, respect to K0. K0 is the band of frequency. See, it's the band of frequency where you take the measurement. I just want to emphasize this negative frequency, because if you take the complex conjugate of the solution, we get exactly, because it's scattering problem, we get exactly the complex conjugate of D plus at K is exactly D plus minus K. It's exactly the L1 between 0 and K0, just different way to write it. So this means that if K0 is very large, if you take measurement at very large band of frequency, and this K0 is larger than one of the, for example, the error on the boundary, then you have the Lipschitz stability. You have Lipschitz stability. So the problem, the inverse median problem of multifrequency is well posed. So here I will talk a little bit about the proof. So the idea started with the paper of Shen and Rocklin. This is explained well in the PhD thesis of Yu Shen, in Yale University. So this is the idea. The idea is high wave, high frequency asymptotic expansion of the solution of the Helmholtz equation. And the idea is in 1D you can use Liouville transformation to it's one of the obstacles to derive the high wave, high asymptotic expansion of this function is that you have the product between the frequency and the refractive index. And the idea of Yu Shen and it's not their idea, but they use that, is to transform this equation into something like this. Okay, so this is the idea. Once you separate the refractive index with from the frequency, you can really do asymptotic expansion for high frequency, and this is what they did. And they derive these asymptotic expansion, and you have the P plus and P minus are the impedance function. We see the first term of the asymptotic expansion is the square root of the index of fraction, and the second term is something that depends on Q, 1 over K. And if you take the complex conjugate of P plus minus P minus, you get exactly something that is bounded by constant over K power M, with M is the regularity of the median function. So this for K large enough. So this is the K idea of their trace formula. So we derive the trace formula from this term. Talk about the trace formula. This is again proved in the work of Yu Shen and Vladimir Rocklin. So this is the trace formula. You have a relationship between the impedance function and the median function. If you have, of course, the whole frequency, if you have the band of frequency, you have the linear relation between the impedance function and the median function. Of course, here you cannot use this trace formula to reconstruct Q. Of course, because you X here, you want to recover Q inside the interval 0, 1. Okay? But you only have P plus and P minus outside of the interval 0, 1. Okay. So you cannot use this trace formula directly, but this is the idea. So because of this asymptotic expansion, you can truncate this trace formula. You see, if you take you consider only the impedance function on interval of frequency minus K0, K0, you have a very good approximation. This is something constant power over K0 power minus M minus 1, which is very good approximation of this trace formula. So their idea is to, they really found an answer to this question. At fixed frequency, what can you reconstruct from the median function? What can you observe? Okay. So they came up with this trace formula. And the idea is to couple this trace formula with the impedance of the Riccati equation. So they assume that you have measurement between 0 and K0 minus K0, K0. And we define that what we call the observable part of the median function, index K0, as the solution of this system. So P plus and P minus is exactly the Riccati equation. I just substitute Q by QK0, and I truncate the trace formula. Here you have the whole trace formula. I truncate the trace formula. But you know here, you see here that you have a good approximation of this trace formula if you take a large band of frequency. So this is the idea. They use this idea to reconstruct numerically the solution. And what we did is somehow derive the stability estimate for this observable part. This is what we did. So this is the idea. So we the P plus. So they took they give some approximation between the true function, the true medium function, and the observable part. And for K0 large enough, you have very good approximation. This QK0 will give you a very good approximation of the real medium function. And you here is this power K0 power M minus 1. And we use this, so if we use this result, combine it to the stability of this Riccati trace formula, truncated trace formula, to derive the stability estimate. And this is what we did. This is our result. To Q and Q tilde satisfying the same assumption, the same notation. D and D tilde are the measurement related to Q and Q tilde. And we proved that for K0 large enough, the observable part defined in this Riccati truncated trace formula is stable with respect to the measurement. So assume that this constant depends only on M, which is the radius of the ball. We're looking for the solution, and Q0. So we have linear stability of these observable parts. This is what we expect. We expect that the observable part is something that we can reconstruct in a stable way from the measurement, model measurement. So if you combine this result with this result, you will get exactly the stability result I give here. Okay. This is what we have done. How much time is left? 5 minutes. So that's the idea. So probably I'll move to what we want to do in the future. The future that for the inverse source problem, we want to consider inhomogeneous media. We transformed the inverse source problem to a signal inverse problem, try to reconstruct the source function from its Fourier transform. But this idea will not work if you have inhomogeneous media. And of course, if you have, for example, trapped rays inside the media. So we need somehow geometrical assumption on the media to perform the same analysis. And also we try to generalize what we have done in dimension 1 to dimension 2 and 3. And of course, again, we need some geometrical assumption on the medium function. Of course. Also, I forget to mention that the 1D problem, you can reconsider the analysis of the 1D problem can apply for the radially symmetric medium function too. And thank you for your attention. I just want to advertise for this conference in Grenoble, and this is related more to the talk of Guillaume. This is the multi-wave imaging, all different kind of multi-wave imaging. This is GDR on the conference. And the idea is to invite half mathematician, half physicist, and try to get them together and discuss this new type of inverse problem. I hope you can attend this conference. I think you can actually present is the deadline. The deadline is 30th of May this month. You can give a talk of 15 or 20 minutes, and we can provide also financial support for the young researcher. Please visit this website. Thank you very much for your attention.